This project was done together with my teammates at the MediaEval 2020.
Can you confirm that you started hearing something?
Yeah,
it worked.
Yeah? Okay. Just let me know if you want the audio louder or
Presenting
anything.
our work enhancing encoder-decoder architecture for visual question answering on gastrointestinal images. This project was done together with my teammates at the MediaEval 2025 workshop. Now, for our motivation and related work, we noticed that very few works have applied encoder-decoder models to VQA. Our main reference was InstructBlip from 2023, which already combines a visual encoder with a T5-based language model. And we wanted to see how far this idea could go for GI images. So, why did we choose this architecture? Now, most VQA systems today use decoder-only models like GPT or QN because they're flexible for text generation. And we wanted to explore encoder-decoders since their encoder can read the whole input bidirectionally, helping them understand both the image and text more globally. This is useful in medical settings where you need accuracy, not just fluent text. Of course, the downside is that the decoder part can be weaker for long or multi-step reasoning, but we'll come back to that later. Our model is InstructBlip T5XXL, a large encoder-decoder language model paired with a vision transformer vision encoder. The goal was to see if this encoder could actually extract better visual features than what decoder-only models usually rely on. We fine-tuned the model using low-rank adaptation, which lets us update only a few parameters instead of retraining the whole model. We trained for 10 epochs on an A100 GPU with a learning rate of 5 times 10 to the minus 5. We didn't use data augmentation because medical images are sensitive to distortion. We also limited each question and answer to 55 tokens since most of them are short. Now for the results, on the public test sets, our model reached 73.18% accuracy, which is quite competitive. For comparison, MediaEval scored 78.6% and Nguyen-Thuy 2.5 vision language scored 80.6%. Even though Nguyen had the highest accuracy, our Rouge and BERT score metrics were quite close, meaning the model still produced coherent and relevant text answers. For the private test, the performance dropped slightly. Well, it's still acceptable. This was expected because that test set is harder. It includes more complex questions and images from youth hospitals outside of Norway's VQA-X1 dataset. Different lighting, texture, and camera types created a domain mismatch, so the model struggled more with unseen visual styles. Now looking deep into the results, the model works well on simple or single-part questions, but it performs worse on long or multi-part ones since encoder-decoders have a weaker decoder for long dependencies. Still, it shows that encoder-decoders are viable for specialized, non-interactive medical VQA, especially when precise understanding is needed. From the results, we noticed a few key takeaways. First, the encoder-decoder structure clearly helps the model understand the image-text relationships in a more structured way. Since the encoder reads all input tokens bidirectionally, it captures the full context before generating an answer. This makes it strong at short and factual questions, where clear structure matters more than long reasoning. Now, secondly, the model achieves higher syntactic accuracy, meaning its answers are often better organized and grammatically correct compared to decoder-only models. Now, as you can see in the picture, MediaEval's NLP matrix are mostly lower than InstructBlip, which reflects the advantage of encoder-decoder architecture in syntactic accuracy. However, looking at this graph, you can see that our model's accuracy remains low. Now, the downside is that it struggles with long or multi-part questions, where the decoder has to keep track of long dependencies. The vision encoder is also a weak link compared to P1s, since it lacks contrastive pre-training and diverse visual data. Now, these insights show that while encoder-decoders may not dominate yet, they still have strong potential in tasks that value structure and clarity over conversational flexibility. Looking ahead, our next step is to make the model more adaptive and robust across question types and visual domains. We plan to apply contrastive learning to improve the vision encoder. This will help the model better align image and text features, recognize visual similarities, and generalize to new hospitals or camera resources. Next, we'll train by complexity order, starting from simple questions and gradually move to more complex ones. This easy-to-hard approach helps the model build reasoning progressively, learning basic concepts first before tackling multi-step or ambiguous cases. We'll continue exploring decoder enhancements for long sequence reasoning and expand to more diverse datasets to further reduce domain gaps in medical imaging. So that's the end of our presentation. Thank you for listening. If you have any more questions, you can contact us at these emails given in their slide.
All right.